Most engineers picture a processor as something fairly simple. You apply power to the core, it runs, and it draws some amount of current. But inside a modern processor, the physics is far more complex. Take an older microcontroller as an example. It operates at clock frequencies of a few tens of megahertz, contains only tens of thousands of transistors, and its current consumption changes relatively smoothly. As a result, the requirements for its power delivery system are fairly modest. A modern processor is a completely different story. It contains billions of transistors. Even if only 0.1% of the logic switches simultaneously, that's still millions of transistors changing state at the same instant. Every time a transistor switches, it charges or discharges the capacitance of the logic nodes it drives. For a single transistor, the required current is negligible, but when millions switch simultaneously, the result is enormous transient current spikes. For today's processors, current demand changing by tens of amperes within just a few nanoseconds is completely normal. For example, core current can jump from 50 amperes to 90 amperes in only a few nanoseconds when large compute units or cache blocks become active. At the same time, the processor core typically operates at around 1 volt. Under these conditions, even the tiny parasitic inductance of PCB traces, vias, package leads, and power distribution paths creates noticeable voltage droop. At this level, power integrity becomes a battle for just a few tens of millivolts. That's why the power delivery network, PDN, of a modern processor is often far more complex than the entire power supply subsystem of many electronic devices. If you found this video useful, give it a like, subscribe to the channel, and check out our other videos on electronics design and hardware engineering.